The selective capture of propyne from mixtures with propene is important in the context of preparation of polymer grade propene feedstocks. Such separations are normally envisaged to be carried out in fixed bed adsorbers, and for most MOF adsorbents, the selectivity is strongly in favor of propyne, and therefore the desired propene with purities required for polymer grade feedstocks can be recovered in the adsorption cycle. Most commonly, the separation of propyne from propene is driven by adsorption selectivity. More recently, there has been increasing attention paid to mixture separations in which deliberate use is made of intracrystalline diffusional influences to improve the separation performance in fixed bed adsorbers. One such example is the use of SIFSIX-Cu-TPA, an anion pillared caged MOF described in this paper, Chemical Science, that is just online. In this paper, it is demonstrated that the separation performance of SIFSIX-Cu-TPA is rather special in that intracrystalline diffusion influences serve to enhance the separations dictated by mixture adsorption equilibrium. Let's examine the synergistic separations of propyne-propene mixtures using this MOF. The separations of propyne-propene mixtures in fixed bed adsorbers using MOFs is described by three separate parameters. The first one is the adsorption selectivity. Normally, the adsorption selectivity is calculated using the ideal adsorbed solution theory of Myers and Prausnitz. In addition, if there are intracrystalline diffusion influences, two other factors come into play. The first one is the diffusional selectivity that I define as the ratio of the Maxwell-Stefan diffusivity of component 1 with respect to the Maxwell-Stefan diffusivity of component 2. Components 1 and 2 are propyne and propene respectively. The third factor that comes into play is the severity of diffusional influences that is quantified by the ratio of the Maxwell-Stefan diffusivity of guest species I to the square of the radius of the crystallites within the adsorbent particles. We may envisage three different scenarios. we could have the adsorption selectivity greater than unity and the diffusion selectivity also exceeding unity. In this case, we talk about synergy between adsorption and diffusion. In the second scenario, we have the adsorption selectivity greater than unity, but the diffusion selectivity of 1 with respect to 2 is less than unity. And in this case, we have anti-synergy between adsorption and diffusion. It is also to be noted that for diffusional influences, either synergistic or anti-synergistic, to have any influence on the separation performance, we should have a reasonable value for the severity of diffusional influences. This parameter here should be small enough to allow diffusional influences to be effective. Indeed, if this ratio is very large, there are no diffusional influences. Let us examine propyne-propene separations using SIFSIX-Cu-TPA by looking at transient breakthroughs in a fixed bed adsorber. The experimental data on the transient breakthroughs for 1090 propyne mixtures in a fixed bed of SIFSIX-Cu-TPA, as reported in this chemical science paper, is shown here with these red circles. Transient breakthrough simulations, ignoring diffusional influences, are shown by the continuous solid black lines here. We note that the experimental data on the transient breakthroughs show that the productivity of purified propene is larger in the experiments than anticipated by a model in which diffusional influences are considered to be of negligible importance. The conclusion to be drawn by this comparison of transient breakthrough simulations without diffusional limitations and experimental data would lead us to conclude that there is synergy between adsorption and diffusion, and this synergy is described in detail in this publication. To illustrate the importance of the synergistic influence of intracrystalline diffusion, I show here a comparison of two types of breakthrough simulations. The one in black is the same as the one shown here. Here, the intracrystalline diffusional influences are considered to be of negligible importance, and the breakthroughs are sharp. The simulations in red are simulations in which we have a diffusional selectivity of 5 in favor of propyne, and the severity of diffusional influences for components 1 and 2 are described by these two parameters. Due to the synergy between adsorption and diffusion, the gap between the breakthroughs of propene and propyne is wider than in the simulations in which intracrystalline diffusion influences are considered to be negligible. The net result is that the synergistic influence of diffusion would lead to a higher productivity of the desired propene product that is recovered at the exit of the fixed bed adsorber during the adsorption cycle.